So for section 3.2, it's going to be conditional probability. So conditional probability is going to be the probability of an event happening given that another event already happened. So sometimes this will change the probability and sometimes it will not. So the conditional probability of an event B occurring given that another event A already occurred is going to be denoted like this. So it's the probability of B such that A already occurred, and we can read it as the probability of B given A. So some event A already happened, and we want to determine the probability that event B will now happen. So let's see an example here. So two cards are selected in sequence, so that just means one after another. From a standard deck of 52 cards, find the probability that the second card is a queen, given that the first card is a king and it's not replaced. So this is going to be conditional probability. So I'm going to let Q equal the event the second card is a queen. And I'm going to let K is going to be the event the first card is a king and not replaced. So that means what we're looking for is the probability of Q given K. So we're looking for the probability the second card is a queen given that the first one was a king and it was not replaced. So this is just going to be essentially a ratio here. So we have to figure out how many times we can select a queen divided by the total number of options of choosing a card. So there are 4 queens in the deck. So that's going to be 4. And then originally there's 52 cards in the deck. We removed a king, so there's actually only 51 cards left. So it's going to be 4 over 51. So we call that that denominator, or 51 here. We say that we reduced the sample space because the king was removed. So that's actually our answer. Answer is 4 out of 51. Or if we want it as a percent, or rather as a decimal, it would be 0.078. So either 4 out of 51 is the answer or 0.078. Okay, let's do another one. So suppose you flip a coin and then roll a 6-sided die. We want the probability of rolling a 6 given that you flipped a tails. So I'm going to let 6 be the event rolling a 6, and T be the event flipping a tails. So that means we're looking for the probability of rolling a 6 given that we flipped a tails. Okay, so for this one, clearly flipping a tails does not affect rolling a 6. So this is actually going to be equal to the probability of just rolling a 6. So the probability of rolling a 6 on a fair 6-sided die is just 1 out of 6. So these are actually called independent events, which we'll formally define on the next page. But independent events, they're independent of each other. So rolling or flipping the tails does not affect rolling a 6 on the die afterwards. So just like we mentioned, the definition here of independent events, we say that 2 events are independent when the occurrence of one does not affect the probability of the other one occurring. So what happens here for the probability of B given that A occurred? If B and A are independent events here, then the fact that A already occurred does not affect the probability of B happening. So this would just be the probability of B, which is what happened in the previous example. And events that are not independent are just called dependent. So what that would mean is that the probability of A given B, this would change the probability of B, so this does not equal the probability of B, which we saw in the first example that we did on the previous page. So let's do this example right here. So let's determine whether or not the events are independent or dependent. The first one is selecting a king from a 52 card deck without replacement and then selecting a queen. So what we want here is the probability of selecting a queen given that we selected a king and did not replace it. So we actually did this one on the first page. We said there was 4 queens left, but only 51 cards left because it was without replacement. So now we're going to use this definition up here. We're going to see if this is equal to just the probability of a queen. So the probability of just picking a queen out of a 52 card deck is 4 out of 52, right? 4 queens, 52 total cards. So since the probability of choosing a queen, given that we chose a king without replacement, does not equal the probability of choosing a queen, these are dependent events. So hopefully this was pretty obvious. We chose a king and we did not put it back. So clearly that's going to affect the probability of choosing another card after that because we didn't replace the first one that we chose. For this next one, let's say we are selecting a king from 52 card deck with replacement this time, and then selecting a queen. So similar setup here, we're looking for the probability of choosing a queen such that we already chose a king and did replace it. Sorry, we did replace this one. So if we replaced it, there's going to be 52 cards again. So the probability of choosing a queen is going to be 4 out of 52. So that was the probability of choosing a queen, given that we chose a king and then replaced it. Now the probability of just choosing a queen, once again, this is still 4 out of 52. 4 queens, 52 cards. So this time the probability of choosing a queen, given we chose a king and replaced it, it does equal the probability of just choosing a queen. So choosing the king and replacing it did not affect the probability. So this means that these are independent events. So this brings us to one of the important rules here. It's the multiplication rule. So the multiplication rule is going to help us find the probability of 2 or more events occurring in a sequence. So probability of 2 or more events occurring in a sequence. So once again, a sequence just means one after another. So the probability that 2 events A and events B will occur in a sequence is going to be the multiplication rule, which is the probability of A and B. So you can kind of read that and as in and then. The probability of A and then B occurring equals to the probability of A times the probability of B, given that A just happened. So we have that conditional probability in here. And if 2 events A and B are independent, this actually simplifies a little bit. The formula becomes the probability of A and then B occurring equals to the probability of A times just the probability of B. So based on the definition of independent events, if B and A were independent, then that means the probability of B given A occurred is just the probability of B. So it simplifies a little bit to that one. Let's do some examples here. So for the first example, let's say 2 cards are selected without replacing the first card. So I'm just going to underline that right away. It's going to be important. 2 cards are selected without replacing the first card. We want to find the probability of selecting a king and then selecting a queen. So this is going to be the probability of selecting a king and then a queen without replacement. So the probability of selecting a king and then a queen is going to be the probability of a king times the probability of a queen, given we just chose a king and did not replace it. So the probability of choosing a king, there's 4 kings out of 52 cards, times the probability of choosing a queen, 4 queens out of, now there's 51 cards because it was without replacement. So we have to multiply these together. So multiply numerators, we get 16 Multiply denominators, we get 2,652. So this is going to be about 0.006 or 0.6% chance, which is pretty low. So there's a 0.6% chance of choosing a king and then a queen without replacement. Next one, 4 cards are selected without replacing any of the cards. So without replacement again. So we want the probability of selecting 3 spades and then a heart without replacement. So I'm going to write this as the probability of a spade and another spade and another spade and then a heart. So 3 spades and then a heart. Not the best use of notation here, kind of looks messy, but that's all right. Okay, so we just go in order again. So the probability of the first card being a spade, there's 13, so these are the suits. There's 13 of each suit in a deck. So there's 13 spades out of the 52 cards. So this is without replacement. So without replacement, probability of selecting another spade, there's only 12 spades left because it's a without replacement, and there's 51 cards left. For the third card, it's selecting a spade again. Now there's only 11 spades left and 50 cards left. Lastly, for choosing a heart, there's still 13 hearts left, and now there's only 49 total cards left. So we would have to multiply all this together. We would get 17,160 divided by 6,497,400. And this is approximately 0.0026 or 0.26% chance. So once again, pretty low probability of this happening. Last one for this, a coin is tossed and then a die is rolled. We want the probability of tossing a heads and then rolling a 6. So we want the probability of tossing a heads and then rolling a 6. So this is going to be the probability of tossing a heads times the probability of rolling a 6 given that we tossed a heads. So these are actually independent events, right? We already said that doing one of these does not affect the other one. So since these are independent events, this is just going to equal the probability of a heads times the probability of rolling a 6. Probability of a heads, assuming it's a fair coin, is 1/2. Probability of rolling a 6 is 1/6, 1 out of 6. Multiplying these, we get 1/12, which is about 0.083. So there is a 8.3% chance of this happening. Okay, for the last thing here, so something that's going to come in handy to use if you are doing a problem and we see something that says you're looking for the probability of at least 1, that means it could be 1, it could be 2, 3, as many as there are trials. The shortcut way to do this is the probability of at least 1 success is 1 minus the probability of no successes, or 1 minus the probability of none. So we'll see this in a few seconds here. So for this example here, for an ACL surgery, the probability of success is 0.95. So that means for one surgery, there's a 95% chance that it's successful. We want to find the probability of the following. So the first one here we want the probability that 3 surgeries are successful. So I'm going to let event E, it's going to be the event a surgery, just a single surgery is successful. So we want the probability that 3 are successful. So that means we want the probability that the first one is a success and the probability that the second one is a success and that the third one's a success. So that's actually the multiplication rule. It's going to be the probability that the first one's a success times the probability of another success times the probability of a third success. So we already know this probability. we're given it right up here in the problem. We know the probability of the success is 0.95. So plugging this in for all of them, it's going to be 0.95 times 0.95 times 0.95. Multiplying those together, we get 0.857-ish, or 85.7%. So there's about an 85.7% chance of 3 surgeries being successful, given that there's a 95% chance that 1 is successful. Okay, next one, we want the probability that none are successful. So we have to be kind of careful here. If we let E up here, we said E was the event a surgery is successful. That means E complement is going to be the event a surgery is not successful. So looking for the probability that none are successful. Another way that we can reword this to kind of help us figure out what to do is we're looking for the probability that the first one is not a success, and that the second one is not a success, and the third one is also not a success. This is going to be the multiplication rule. It's going to be the probability of E complement times the probability of E complement times the probability of E complement. So it's a little bit tricky, but you just have to use that multiplication rule again for all 3 events happening in a sequence here. Okay, so the probability of E complement, we have to remember this is 1 minus the probability of E, which is 1 minus 0.95, which is 0.05. So the probability that a surgery is not successful is 5%, because the probability that it was successful is 95%. So now we plug all of those in. That's going to be 0.05 times 0.05 times 0.05. We multiply all of those together and we get 0.0001, or 0.01%. So there's a 0.01% chance that all 3 of them would be unsuccessful, which should make sense that it was so low because the probability of 1 success was so high. Last one here, the probability that at least 1 is successful. So here's that phrase, at least 1. So that means we're looking that we could either have 1 success, 2 successes, or 3 successes, right? Or we can use that shortcut that we mentioned up at the top. The probability of at least 1 success equals 1 minus the probability that none are successful. So probability of at least 1 is 1 minus the probability of none. We actually just did the probability that none were successful in the previous one. So this is going to be 1 minus 0.0001, because that's our answer from the previous one, 0.0001 for none successful. Subtracting these, we get 0.9999, or 99.99%. Which is huge. The probability of at least 1 success is almost 100%, 99.99%. Okay, so that's actually it for section 3.2 with conditional probability and the multiplication rule.